welcome everybody to the new year and lecture 10 of Databases and Information Systems, the course that can also be taken as information retrieval. Overview over this lecture, I will say something about your experiences with exercise sheet 9, for which you had 4 weeks. It was the second part of web apps. The regular week, just remember it's 4 weeks since we last saw each other. 1 week as usual, the 2 weeks of vacation, and then we dropped the first appointment this year for reasons. I will show a demo of some of your web apps and also the master solution, and the official course evaluation has started, and I have a slide on that with more information. Then afterwards today we start something completely new, linear algebra. So it's only 3 more lectures with content, and they will be about the magic of linear algebra, vector space model, word embeddings. We start it's really something completely new. So there is some connection, of course, to what we did earlier, but new topic. And you will see it. So first experiences with the web apps exercise sheet. So it was quite a bit of work. You also had a lot of time, but those who did it, not very many, I should say. I also have a slide on that. Liked it a lot. The sheet was very complex. Complex, I think, is the right word. Not hard, but just so many things. So complex, right? The complexity here comes from these many different things. Server side, network, client side, JavaScript, database stuff. You have to put all of this together, and for that you have to understand what it is, how it works. But best sheet ever, very interesting, motivating to see the website I created. Super cool exercise sheet. I feel like I learned a lot, enjoyed the freedom of doing things. We gave you templates, but otherwise, you had a lot of freedom and lack of hand-holding. Interesting wording, very interesting, fun, but surely a long one. Nice to see all the hard work paying off. I mean, in this sheet, really everything came together. We will see it when we see the demos. I had major issues with the query speed, which I couldn't fix. And some people did not manage to do the relations. Okay, let's just look at a few, as I promised. And let's maybe start with this one. We've prepared 3 and our master solution. So here's one. Okay, let's Happy New Year. Okay, it's a film directed. I'm just typing random things. So this is the website. It's pretty fast, right? And I should also be able to make mistakes. So I typed happy with 1 P. So, I mean, that's a lot of data. I forgot how many entities, but a few hundred, I don't know, even millions. I don't know. Do you know it? How many entities did we have? It's instant, right? It's really not bad. So here, show relations. Okay. A little bit buggy, but works. So I typed twice. So here you see the database, the Sparkle query, which just gives all the triples of this movie here. If I click again, it may be, and if I click on here, I get to the Wikipedia page. Okay, nice one. Here with another one with a nice logo. Let's type this one and search Freiburg. Okay, I type something, and maybe I type, so I make a lot of typos, and I still find it instant, super fast. More details. Here I get to the web page. If I click on this, so I get to the web page. No relations here. So also pretty nice design. And here is another one. Did I forget one? Number 2, right? The one in between. Okay, I had this one twice. Here's another one. Okay, you know this from the older times. You are the 1000th visitor. You want a free. Okay, nice one. And let's, I don't know. Let's type some countries here. India. So also instant, right? Very. Okay, China. So here I have. I can have 2 things. If I click on here, I get I get to the web page, and if I click on here, I get the triples from the. So everything is super fast. Of course, that's what we have worked hard on in the last lectures, an exercise sheet, and it worked fine. This is the master solution. So there were some Easter eggs in them. For example, if I type, and let's look at how those came to pass. Okay, this does not work for some reason because okay, I have to start the master solution. Yeah, let me just show you how you start it. Server pi, I want qgrams with 3, I want synonyms, I want, these are the list of entities. Maybe let's look at them. I wanted to know how many there are, and just so that you remember. I think I'm in the, I have to go to folder 9. No, I'm also not in the right folder. Okay, I have to go back to, yes. Now I'm in the right folder. That was one of the input files. There was also one with the triples, and let's just look by typing less minus n here, how many we had. So, so it's 1.5 million, quite a lot, right? It's not, and you see a lot of information here, also synonyms if you go further down the list, and let's go back to the command line which I had here. So I'm running the server, I'm saying on which port it should run 8080. I'm giving this list of entities from which it builds this 3-gram index because I specify 3 here. Minus S says also find things if I type synonyms. And for the relations, I've built a database and there's also in there the code for translating Sparkle queries to SQL queries on that database. So quite amazing that we're able to do something like this in sheet 9. And let's just run it. Now it's building the index. It takes a while, but pretty fast, and just 5 seconds and it's there. So let's just reload this. Yep, and now we should be able to, so if I type USA, I get the United States, so that was via synonym search here, right? So it was first, even though I didn't type the entity name is United States of America. And let me type snow. And some of you found this. Now it's snowing. We talked about vulnerabilities in the. So now I can, in case you didn't see this. So those of you who did the exercise sheet there were quite a few of those in the. Let me turn around. Okay, this one doesn't work. There was. Not all of them work. Okay, matrix. That's another one. And I will show you in a second how it happens, and maybe one, I don't know, maybe, okay, asteroids, and now I get, okay. Now I get, now I have a video game here. I can destroy. There's a highest code down here. So what happened? Apparently some code got injected in our web page, and there are actually more. So if you didn't do the exercise sheet, at least look at the master solution and try to, so if you have a security problem, then you can do anything, right? One more here is, I think, Okay, now we have a whole video game here, gorillas, in case you didn't know it. And there are more. Okay, now you have a whole video game right here. I have 2 gorillas here and have to throw a banana here to hit the other gorilla. In case you haven't played it, or in case you have, what angle do you suggest? I have to specify at which angle I throw this and at which speed. So let me try 70, which is a rather steep one, and I'm a bit lower, so maybe 80. I don't know, I'm not a gorilla professional, but okay, that's pretty steep, and okay, that was not, and now it's the others, so maybe 70 and 85. One more try. Okay, you see the point, that's the game. And Is it coming down? No, it was too fast. Okay. Let's. So how did this happen? Well, let me show you this. And let me. This is the file which I showed you earlier, the TSV file. And if I grab for something particular, for this thing here, so there are image tags in there. And actually this gets harder every year to actually inject JavaScript. So what's happening here, this is the description of the entity which is shown in the web page. And as you see, it has it says precipitation in the form of crystal ice flakes, but it also has other stuff before which you don't see. And what is it? It's actually an empty image. So it's an image which you don't see, nothing. So like these hidden pixels in mails or something. And when this image gets loaded, it also loads, it also executes this JavaScript, which in fact executes code. In the past, it was much simpler. You could just write script here, so JavaScript tags, but most browsers nowadays say, no, this is certainly not what you want here, but you can still do it. It just gets harder every year. So here you're loading an empty image, and when the image has loaded, you start some JavaScript which creates an element and loads it. And let's just see, we can actually look at the JavaScript by let me maybe just, is it here? Yeah, here should be the link. Yeah, for example, this one. They are also hidden here. I could have loaded them from any way, of course. Okay, forbidden. And so here I have asteroids, JS. Which one did I want to look at? Oh, I think it was on the slides even. Yeah, BSOD, that was one of them. Some of you actually found it and also looked at the code. So now I have, this is not even by us, some are by us, some are by others. So now I have whole JavaScript which is loaded into the page. This one was particularly funny because it has these funny comments. Yeah, it's on one line. Well, so somebody wrote this code, had strange comments. Yeah. So the easiest way to mess with someone's console. Yeah, so you can look at those if you want to. Here's your, so there are a few more if you want to, just try them out. Here are some of your reactions. Wow, the snow animation is cool. I really like the snow, and the asteroids game was fun. Asteroids, high score 340. Harlem Shake behavior, that would be loud, so try it out yourself. It's very funny. The script comments are entertaining. We just saw one. Gorilla shocked as I tested it with a friend, and he sniped me with a banana. Microsoft. Oh yeah, let's see the maybe let Microsoft one. Let's see if it works, and then we go on with our contents. Although this is fun, but this is so fast that we can just do it again. Research 8080. Oh yeah, that's the Windows one. Yeah, okay, if you type Windows, you get the... Nice. Okay, so let's go on. One more slide, which I promised on the third exercise sheet. So to say it again, it's really so cool that just a 9 exercise sheet, you can do something so complex. And not only that it connects many things, it's also the typical things when you write a web application nowadays, right? You have server code, you have network code, you have code on the client, a lot, typically JavaScript, and you have some form of database from which you get data. So that's a very typical setup, which is exactly why we did it the way we did it. Will this be on the exam? So will you do you have to code web apps on the exam? Maybe some of you thought, well, yeah, we should have done the exercise sheets, but it won't be on the exam anyway. Of course it will be on the exam. There's always a question in the exam that involves writing server code, HTML, JavaScript. And not only you have to write it, you have to understand how this works. If you have done the exercise sheets, it will be easy. Of course, you don't have to write a flight simulator in the exam. Out of experience, I don't see, and we don't see, if you didn't do this, and now for the exam, you just look at the slides, you don't learn this stuff from looking at the slides. I think most of you who did the exercise sheets know what I'm talking about. If you listen to the lecture, you say, yeah, nice, I understand how, but you have to do it. You have to actually do it to understand all these intricacies, how it actually works. I mean, that's true of most everything in life. You have to do it to understand it. So just looking at the slides and then hoping that you can do the exercises, the exam, it won't work. And again, we are speaking from experience, because we have always participants in our exam who, I mean, you see what they do. Either they don't, also in oral exams, it's the same, you get the same kind of questions. They make the impression of having never written a web app themselves. And it shows you don't get the points, so don't be one of these people. So even if you didn't do it now, at least do it at some point, at least do it when you prepare for the exam. Otherwise, there will be tasks about this, you won't get the points, which would be a pity. And very few people, some people did the number 8, very few people did number 9. So this is kind of a separate topic, how few people do the exercises. But I've mentioned this already. So the official course evaluation, you should have received an email yesterday. Who here in the room or on Zoom hasn't received an email? Okay, one person, 2 persons. It always happens. So we have a forum evaluation. Just if you are interested to take part in the evaluation, just post to that forum on Daphne. Let me just quickly check whether it's yeah. Okay, I haven't logged in here for a. Yeah, there it is. Evaluation, just say I didn't get the email. Of course, if you don't want to participate, you don't have to. So, but please participate and take your time for it. I mean, you have been listening to 9 lectures already, another one, 4 more. You can spend 15 minutes on the evaluation. And of course, be honest, be concrete, don't say something super abstract, and fair. Even if you have criticism, try to be fair. Very important. And this entails one thing which we added this year, because the exercise sheets are voluntary. There will be one question which asks you, did you do the exercise sheets? And I mean, it's anonymous, so please be, if you don't be honest, you are messing up the whole evaluation. It's not a super detailed account you have to give. You just have to say, I didn't do them. Or you have to say, yeah, I did a few, or I did most of them. And we are very interested in that, so that we can find some correlation. So please be honest with that answer. It's anonymous. We don't know who says what. It's important for us to understand what's going on. Yeah. As usual, there are scores. Of course, if you liked it, give a high score, but the free text comments are particularly interesting because they give more information. And yeah, why not do it right today after the lecture? It's just 15 minutes. Actually, we condensed this thing some time ago so that it's not so many questions anymore. It used to be way too many questions. Now it's a relatively short form. So it should be easy and fun. It's nice to give feedback. So that's the super last deadline. So if you miss that deadline, there's nothing we can do. It's a centralized evaluation. So we are not running it. University, a team at university is running it. If it's closed, it's closed. We can try, if somebody didn't get the mail, to write them. Sometimes they, in the last years, has been a very nice team, very forthcoming if there are problems. And that's what I just said. If you didn't receive an email, just post in the subforum. Okay. So, new content. But before we do the new content, I kind of promised, and I want to do it a little bit. We had to rush, or I didn't rush, I just left out a part of the last lecture, which is important and relevant, and I just wanted to spend 5 to 10 minutes on it. And it was about Unicode. So this is now still from we will start with the new stuff soon in 5 to 10 minutes. Unicode. And I mean, I hope you remember it, at least from the lecture or from the sheets. It was, how do you encode funny characters? I mean, we have the typical characters, we have the more common ones, at least in the Western world, like A umlaut, Greek letter, euro, a new symbol, or smiley face. How do you encode all these characters such that it works for everyone? And there is a scheme called Unicode, which is around for many decades now. And so I'm just recapping a little bit so that I can show you the thing which I didn't show last time. They're basically, so these are the slides from the, I hear someone talking, please don't talk. So there are basically 3 schemes. One is always use 4 bytes. That's easy. I mean, then you always have 4 bytes. It's easy to parse, but super wasteful because most characters, like the ordinary ones here, which we see on this slide, just take 1 byte. So yeah, I mean, then there's UTF-6, then there's UTF-8, which uses as many bytes as needed. So very often 1, sometimes 2, sometimes 3, sometimes 4. And then, as always, there is the worst from both worlds scheme, UTF-816, which uses typically 2 bytes, but sometimes 4 bytes. So it has the bad part from both parts. It's variable byte, but still wasteful, because typically you only use 1 byte, and it's used by Java. Yeah, I think this was a bad decision. Java made a few bad decisions. So almost everybody uses UTF-8. Okay. And we explained it. I won't explain this again. This is just how you do the encoding, and it ensures that ASCII characters are encoded in the typical ones, encoded in 1 byte, and only for the... somebody is talking, and I hear it quite... Please don't talk. Or go outside if you need to talk, or wait for the break. Okay, so... and the thing which I didn't show, I wanted to show you now. And if you did the exercise sheet, you probably had some experience with this. I mean, it's a simple principle, but it gets complicated very quickly. And I want to show you. Let's just encoding test.py, and let me write a very simple program which just prints a character here on the command line. And let me just write it here, Python 3 encoding test py, and it types A. Okay, that's simple enough. That's how it should be. So that's just a funny character, A, which uses 2 bytes in UTF-8. And now I just want to show you a few things. There are so many more things, but just to show you what's the problem. So this file is encoded in a particular way, and it's actually, yeah, it's encoded in UTF-8. So this is a program. It's a Python program. How do I know in this Python program how this is represented, right? Is this represented in Latin, ISO Latin? Then it would be 1 byte in UTF-8 or something else. Here's a program to look at stuff. And this is, it's XXD, which just shows me it has many parameters, but I'm not, actually I don't know them. Okay, that was wrong. G1. Yeah, now it's just showing me, now it's showing me the individual characters here in hex code. And here it shows what it prints. So here I can see, so 70 is probably the P, right? Let's just look at that. And that's a very useful program. That's why I'm showing it to you. There are other tools as well, of course, but if you just want to know, okay, what are the bytes of what I'm looking at? And sometimes can also be an output file or something, because something is wrong, and what you see is not necessarily what you get, or vice versa. So here you have this German umlaut. How is it represented? And I can see it. So P here, 70. Let's look at hex code 70. It's not decimal 70, it's hex code 70. Where is it here? Yeah, so it's indeed the P. So this is the 70. And here somewhere we see the quotes. The quotes in hex are 22. And now comes the umlaut, and you see C3A4. Right? So it's represented in 2 bytes. Now let's change that. Let's just pick Latin 1 here, and it's not supported. Okay, maybe ISO 88591. That's the encoding before Unicode, which was used a lot. Not supported. Okay, I'm a bit surprised. That's not what I expected. So I can't ISO Latin 1. Not, and I maybe can't show this. Okay, maybe I should, this is NeoVim, maybe in Vim it works. Let's, okay, the file encoding, there's also, let me set the file encoding to Latin 1, okay. Now it's in Latin 1, and now let me type this again. And now let me look at the file again. Yeah, and now it's just 1 character, right? 22 was the quotes and this. So now it's the same file and it's in E4. And let's just run the program. And what happens now? Yeah, okay. Now it says this is, it's not valid code, which is a funny situation because the Python code is expecting that the things here are encoded in UTF-8, but the file is written in, the file is encoded in Latin, so the program doesn't even run. And this, I could show so many more things. One thing I could do here is actually, how do I specify the encoding? And I always forget this. Now I have to. How do I do this in Python? There's a special syntax for specifying the encoding. Who knows it? It's star coding, okay. I think it's ISO 88, okay. Let's go back here. Now I'm saying the Python program should understand what's written here as, and let me see if it's still the same. Yeah, this is still 1 character, quote E422. And let me see. Yeah, now I can write the Python program and now it's even printing as an A. Okay, which is also surprising because, and now let me do something. How do I actually get this to print as a, okay, this doesn't work, can only contain ASCII literals. Okay. So that's interesting because here's another thing which I wanted to show you. So let me, and then we will be done. Let me go back here and let me go back to UTF-8 here. And I think the file encoding is, now it's Latin 1. Okay, it didn't let me set it, but it accepts it when it's in the other. So now the file encoding is UTF-8 again. And now let's, the terminal also has an encoding. That's what I wanted to show. This terminal assumes that what you send to it, I mean, it just gets a stream of byte from any program, that it's Unicode. Let's just say the terminal encoding is ISO 88851. So now I changed the encoding. Now this here is, let's just look XXD again. This is now 22, yeah. So this is now 2 characters again, my umlaut, because I changed the file encoding to umlaut. So it's now again C3A4, so 2 bytes. And the Python, I told Python, yes, this is UTF-8, interpreted as such. And now I'm running this, and now it's sending the 2 bytes to my terminal, which is interpreting it as ISO Latin. So I get these 2 characters, which should look familiar because you get them a lot in mail, which is somehow garbled up, Yeah, mail is a lot about somebody sends you an email in ISO 88591 and your mail is set to UTF-8 and then it's interpreted in a wrong way. Typically it should be, there should be headers which says what the encoding is, but when you forward stuff, reply to stuff, this very often gets mangled up. I will stop here, go back to the slides maybe briefly. But you see how many things are interacting here. So it's how the program is written here, how Python interprets what's the contents of this file. Then it's sent to somewhere, maybe to a web browser, to a terminal, where it's also interpreted. Then the editor, I'm not showing this, there's file encoding and there is encoding. These are also two different things. So I have already 5 different things here, right? Let me just list them, and then I go on just to tell you how much fun this is. There is how is the file encoded, which I can see with XXD. How does the editor show what's encoded in the file? That's the encoding. How does Python interpret what's written in the file when I run it? And how does the terminal or wherever I send this interpret it? So I have 5. And these encodings can be any combination. So I have, if there are k encodings, I have k to the 5 different possibilities. And so many things can happen, and do happen typically. So XXD is your friend if you want to look at, you have some output, what's really there, because what is shown is, typically does not help you, because what is shown is also already an interpretation. In the different programming languages, very briefly, and then we move on. It's already past 10 minutes that I wanted to spend. So the character length, that's an issue. So if it's encoded in UTF-8, like the R umlaut, which is 2 bytes, is it length 1 or 2? Well, if it's a string in C++, it's length 2 because it's 2 bytes. In Python, this would count as 1 because it's 1 character. It's different in the various languages. In Java, it's just a total mess. So if you have the smiley face, so typically it will give you length 1, but if you have the smiley face, which uses 3 bytes in UTF-8, so 2 bytes in UTF-8 16, it will tell you the length of the string is 2, which is just bad. And then you have all kinds of, and in Python, here's some more. This is what we have seen, for example. If you have the wrong encoding, you get funny stuff. Okay, just so you have seen this, that you're aware of this, if you have problems with encodings, try to look at the raw data with something like XXD. Okay, any questions about that? Otherwise, we move on to a new world, that of linear algebra. Okay. And it's very lightweight today. The exercise is also fairly easy. Please do it, because the next 3 exercise sheets are about using linear algebra. And we will even talk about language models in the last lecture. We will even do one ourselves. And the foundation of all the deep learning and everything is linear algebra, pretty simple linear algebra. So let's start. So far we had inverted all kinds of indices, inverted indexes. Today we will represent everything as vectors, linear algebra vectors. Here's our running example for today. We have 6 documents and 4 words, and they are written in a matrix. So every document is a column here. Document 1 is just the document which contains the word internet, web, and surfing. Document 2 contains internet and surfing, and so on. If a word is contained twice, I have a 2 here. There's a reason behind this particular example. I don't think we will make use of that, but let me briefly explain. We will make use of it a little bit. So internet and web, they are kind of the same they mean a very similar thing, right? We will come back to that at the end of the lecture. They are synonyms, sort of synonyms. Don't mean exactly the same thing, but people use them synonymously. Surfing is what's called a polysem, because it means different things in different contexts. So surfing the web is something else than surfing on the beach. So that's a polysem and a synonym, and these two concepts are generally very important. So different words meaning the same thing, the same word meaning different things in different contexts. Okay, and if you have a zero, it just means that word is not contained in that document, and that will be important later. If you think of larger text collections, there will be many zeros in this matrix, because every document of all the possible words just contains a small subset. In this lecture, we use TF scores. So the 2 says this word is contained 2 times. For the exercise sheet, you will use BM25 scores. I will talk about them again. So this is often called the vector space model, because you represent things as vectors. So in a vector space, words are typically referred to as terms, which is why this thing is not called a word document matrix, but a term document matrix. But that's just terminology. Okay, so retrieval. Let's say we have a query now, and the query is web surfing. Then we can also write the query just like a document, right? It's also, you just have a vector, and wherever you have one of the words, you have a 1, otherwise you have a 0. So this query is like the query for web surfing. And now, let's start very easy. How could you measure the relevance? You just take the dot product. And let's just take the dot product. Let me put this aside and draw something. And let me just, So let me take the dot product between this perfectly straight line rectangle. What's the dot product between these two vectors? Dot product. It's 2 vectors of the same size. So if you have the dot product, so you have 2 vectors, x, which contains of xn. You can also write it in the Zoom chat. I hope someone here knows what the dot product is. So you have 2 vectors, each with the same, and then the dot product is just the sum of the pairwise products. So you just multiply the first components, the second components, the third components, you sum it together. So what's the dot product of these 2 vectors? 2. I see a 2. That's correct. 2. Yeah? So it's this times this, 0, this times this, and this times this, plus 1 times 1, plus 1 times 1, plus 0 times 0. So dot product is really simple. And let's just compute the other dot products. Please tell me, what's the dot product? 1, is correct. Dot product? 2. Dot product? Here? 1, yes. And? 1, yes. And understand, that's written here, that's exactly the TF scores from lecture 2. So if I would do ranking with TF scores, I would get this. Yeah. What did I do? I just looked at my query words, and for these query words, I just summed up the term frequencies. And that's exactly what you get with a dot product. Wherever there's a 0 here, I don't even have to look at the value because it's multiplied with 0. And for the others, I multiply with 1, which means I just, So what this query does is just sum the TF score for web and for surfing, which is 2 here, 1 plus 1, 1, 1 plus 1, 1 plus 2, 1, 1. It's exactly what we did in lecture, actually in lecture 1 already, I think. Okay, very simple. And here's one important thing, and then I will show you a little bit of linear algebra in Python. I assume, linear algebra is so important. It's an integral part of computer science. There's no way you're going to get your diploma if you don't know linear algebra. It's the basis, as I said, of everything deep learning, but also of so many other things. So here's something very basic in case you forgot it or never really understood it. If I want to do what I did on the previous slide, and that's a very typical thing, I want to compute the dot product of one thing with very many things. I want to have these scores. Now, of course, I could just write a loop, compute this dot product, this product. That's not how you do it. You can do it as one big matrix vector multiplication. And let me show that to you. Just so, and so let me write this vector in this form, and you will see in a second why. So that's now my Q. That's now my vector Q, which for some reason here is written in, is it also on this? Yeah, okay. It's written as a capital Q. Okay, I want to write it as a small q, so I just do it like this. And this is it's also a matrix with one row. It's a 1x4 matrix, one row, 4 columns. And let me write this matrix here again. Let me just write it again. 1, 1, 1, 0. I'm just copying it. Please pay attention that I don't make a mistake. 0, 0, 1, 0, 1, 1, 2, 1. And in case you didn't notice, the 5th and the 6th document are identical, but nothing speaks against that, having 2 identical documents in your collection. So this is my matrix, and let me call it A. This is my matrix A, and it has 4 rows and 6 columns. So first rule of linear algebra, don't talk about linear algebra. First rule of linear algebra is if you multiply 2 matrices, and a vector is a special case, these 2 things have to fit, right? You can multiply a 1 times something with a something times something else. This has to be the same, and you will see in a second why. And the result will be a 1 times 6 matrix, which means a flat vector here with. And how do I do the matrix multiplication? Well, let me do it by, let me just put something around here. How you do it, matrix multiplication, I do this times this. And then I just compute the dot product. That's how you do it. I compute the row here. This row with that column gives me the first entry here. And would also work if I have several rows here, then I would also have several rows here. And let me do it in the right color. So this here gives 2. And now let me do it for the next one. Now I do this with this. And this gives me the next entry, which is a 1, which is the dot product of those. And let me do it with one more color, if I have one, maybe in this wonderful red. Okay, and I again take this times this. So this is vector matrix multiplication, also generalizes to matrix multiplication 2, and then the remaining ones I just write them in blue. So now it's this times this, which is 3. This times, let me show it. This times this here is dot product is 1, and this should be something. You shouldn't even think about it. So matrix vector multiplication. It's so important. It's so fundamental. You should be able to just do this. Okay, and this now with a single matrix vector multiplication. And I made a small mistake here because this is actually Q transposed, because here my Q is a column vector, right? So this here is a 4 times 6 matrix, and this is a 4 times 1 matrix, or a column vector. It just has one column, and to be able to multiply it, I have to transpose it. So Qt is the, let me also write that, Qt is transpose. You can always, I mean, this is not really part of this lecture, but I'm just repeating it in case you forgot it. Yeah, transposing is just to make the rows are the columns are the rows. So if I have just a column vector, I transpose it, I have a row vector with the same values. Any questions about this slide, please take the opportunity and ask them now. This is just some very basic linear algebra recap. Maybe something is unclear, then do ask. Okay, and now the question is, how do we do this in Python? Of course, there are many packages in Python, and we will use, and for some reason this, the animation does not work here. Let me just, strange. Okay, should be. So, we use PyTorch. PyTorch is known for use in deep learning, but it's also, you can also do all the kinds of linear algebra with it, basic linear algebra and not so basic linear algebra stuff. So far, we always used NumPy and SciPy, which are still good. You can still use them. Was always a bit strange because you had there's this very old NumPy package which contains very basic linear algebra, and SciPy which contains more advanced linear algebra. So you always needed two. They were not perfectly calibrated to each other. So we used PyTorch, and there we also have the learning stuff which we want later. Of course, PyTorch, there's a lot of documentation on the web. What we did for you here on the wiki, you find 3 links. One is, here's what a tensor is a generalization of matrix and vectors. I will talk about it in a second. So you have to, just to understand the very basic, there's a page. Then if for some reason you have used NumPy in the past, you're very proficient in NumPy, you want to learn PyTorch, here's a wiki, GitHub page which explains that. So yeah, sometimes you have the situation you're very proficient in X, you want to learn Y, which is similar. There are typically pages for that. And we also did something for you, namely a cheat sheet, where we just list the stuff which you need for these exercises and the next 2 ones. I mean, PyTorch is a huge library, it's just huge, you can do so many things with it. It's easy to get lost in the documentation, so here we have just listed the things. For example, to create an empty matrix or a matrix with only zeros or ones. Yeah, so here you see, okay, short description, this creates something only zeros, and then you click on here and you have the exact syntax and semantics. Yeah, so here's this is how it works in principle. You import Torch, you have to, not PyTorch, Torch, you have to install it first, pip install Torch or something like that. Or there's probably also Ubuntu package. You want to create a matrix, and so I said this, let me say it again clearly. In PyTorch, you don't have vectors, matrices, you just have tensors. And tensor is just a generalization of this, right? A vector is just something one-dimensional, a matrix something two-dimensional. You can also have something 3, 4, 5-dimensional. And in deep learning and stuff, you typically have 3-dimensional things also, or even more dimensions. So a tensor is just arbitrary dimensions. So this is a matrix here. So I just have a list of lists. This happens to be the matrix which we have seen earlier, at least the first and the last row. If I want to create a vector, I do it like this. And then matrix, vector matrix product, I can just do it with this syntax. There's also matmul, there are several ways to do the same thing in PyTorch. I think, yeah, here, torch matmul does matrix multiplication and also vector matrix multiplication. I don't know if they mentioned the shortcut here with the add. Okay, so let's just work with this. Let's leave encoding. And this is the code from the last, now we are going back to lecture 2, which was inverted lists. Building inverted lists from a simple collection. So this was the simple example. Let me just make this a little bit smaller here so that we can see most of the files. So this was just 3 test documents, a movie, a film, movie. Let's just look here. We built an inverted index. I hope you haven't forgotten everything. And then we built the inverted list. So now I have an inverted list for the word A. It is contained in documents 1 and 2, which I have 1, 2 here. I have the inverted list for film, which is only contained in document 2, and movie, which is contained twice here, and this was actually from the first lecture, so I have 1, 1 here. Let's just keep it that way for this sheet. 1, 1. Okay, and let me also do a second example here, which helps understanding. So this is now, let's take our matrix, our example matrix here, and let's just write these documents here in Word, because the parsing is done by our code. So this is the document internet web surfing. So let me just internet web surfing, internet, to use the same. The second document is just internet surfing, internet surfing. The third document is web surfing. The order of the words is not important for what you are doing. I mean, there's no notion of order here. It could also be surfing web. This one is internet web surfing twice beach. So let me just internet web surfing beach surfing. Let me write it like this. Now I have surfing twice. I have a score of 2. And then I have twice surfing beach. And let me, the second one, just do it this way. Beach surfing. Okay. And yeah, let's do a little more and then have our break in 5 to 10 minutes. So this is our document. This is the document collection for this matrix. I hope that's clear. Please ask if anything is not clear. And now, of course, I could run my code here. Let me just do that. But I think it does nothing. Yeah, it will just work. Let's also run the doc test, whether it works. -m doc test. And let's maybe change the, just to see whether we are doing the right thing. Let me just change this word here, remove the E. Yeah. Now I removed the E. Now I don't have movie, it's only once here, and I have a new word movie, which is in document 1. So everything works fine here. Okay? Yes, so the doc test works. So back, this is just for the, and that's the collection we're working with now. What I want to do now, and what you should also do for the exercise sheet, it's like the first step. Let's create a term document matrix from the already computed inverted index. So we have already done the parsing and everything. And let's do that. So I guess the first thing we should do is import torch. We want PyTorch. And you will notice one thing, that just by importing torch, and I think this is a bit annoying and strange, but that's how it is. That's not how it should be. I don't know why they did that. So it takes a while, right? Just because you import something, apparently it does some initialization. That's not, I mean, just by importing a library and not using it at all, you shouldn't have to wait, I don't know, how many seconds? Okay, 1 second. So 1 second of your life will be wasted just by and you will do many iterations when, so you always have to wait 1 second just for Torch to initialize. Strange. Okay. Oh, this I forgot to delete it. Here I've already added some things, and actually, let me, yeah, this was not there in the original code. Let me just, we didn't need that for the inverted lists, so let's just do that. The words which we encounter, so here I have a list of words, just a list of strings, and I mean we already have in our code here, this is self, self words, append word. If I have a word that I've not seen so far, it's not inverted list, it's just a dictionary from words to inverted list. If I've not seen it, I add it here. And how do I get the number of words? Well, the number of words is just one way to do it, is it's just the size of my inverted lists dictionary. The other one would be just to count the words vector. And how do I get numdocs here? Look at the code and tell me, how do I get numdocs? I want the number of documents, initially 0. Remember, this is going over record ID. Record ID, yeah. Exactly, the record ID, it's keeping track of the record ID, it's increasing it by 1, which means by the end, record ID should be. And let's just, let's add it to the test, why not? Self terms. No, words, I called it words, okay. And what should be that should be a film movie. Is it correct? Yeah, we will see it. And self-num words should be 3. And self-num docs should be also 3 in our example collection. Just try it. 1 second for Torch. Okay, self is not defined because it shouldn't be self here, it should be II here. Okay. Yeah. The order is not correct. Let's just go upstairs here and check the. Yeah, the words are added in the order where I first see them. So I first see a, then movie, then film. So that was not correct. Here they are sorted, but now it works. 1 second for. Okay, so that was that. Now let's just finish writing the document matrix and then we have a break. But I think you are still with me. So now let's create a term or build. I think we also call it build enough term document matrix. Self, it's a member of a, and yeah. So what do we do? Build a term document matrix, assuming that we have already constructed the inverted index with a build from file method here. Okay. So, how do we do that? Well, let's first start by, so let's call our matrix A, and let's just, let's create a matrix with only zeros. And let's, and let's below here, so that we can already run it, I build term document matrix, print term document matrix A, and let's print it. Okay, this, I think I want to return the term document matrix. Yeah, let me return it and not write it in an internal variable. So here I'm just calling it A for simplicity, and then I print it. Okay, so now I'm just creating a matrix which has as many zeros, but it has already the right dimension, so it should be 4 times 6 if I call it, and let's, and always takes this 1 second. Okay, and then I added time here in the beginning. Okay, looks fine. Yeah, it's a bit annoying that unlike in NumPy, you can style the output. In PyTorch, you always get this object thing like tensor. Now you have a dot, although it's all zeros. So let me do one thing. Let me have a thing here, print matrix. Yeah, actually, this does not have to be a member of the class. I just want to print the matrix in nice form, because Torch is too stupid for it. You can't, I don't know why. Maybe let me just, for each row, print, and what do we... Yeah, that's not what I want. I think I want like 2D maybe, F2. Yeah, okay, let's do that. Let me print the matrix here. Let's see how it looks. Okay, that looks nicer. So, yeah, now I have a matrix with all zeros. Okay, now let's do, as usual, most of the work in coding is preparing. So, given the inverted list, how do I enter the... Well, I think I just go over the words and then I think this is showing me too much information. 4. Yeah, I think I should go over the words in the, for word in self words. Let's go over all words. So I'm going over the words in the order in which they are inserted, which is hopefully the... Yeah. And now I go over the entries in the inverted list. And the entries in the inverted list, if I go a little bit higher, so I'm going over the words, and now I'm going over that list for that word. And I think, let me do it like this, in enumerate words, thank you. And now I'm going over, yeah, let me call it doc ID, it's called record ID above, in self inverted lists for that word. That looks good. So I'm going over the words in order, and I have the word here because I needed to look up the inverted list. I also have the word ID, which should go 0, 1, 3. And now what do I do? What do I write in this line? Suggestions, please. So now I'm at a particular word and I have this here. So how do I write? Yes?
We increment the entry like A,
Yeah.
word ID, doc ID, file ID.
Doc ID. Okay, and let's write.
Increment file not.
Hmm?
I think it should be incrementing, not assigning.
It should be incrementing, not assigning. Very good. I agree. Let's run the code. Something is wrong. What did we do wrong? Can you tell me the line number?
65, enumerate first the index and then
Enumerate and what? Okay, what's my problem here?
returns the two block word ID, word, not word ID.
Oh my, yes. It's first the ID and then the thing. Yeah, if I do enumerate. Thank you. Oh my, index 6 is out of bounds. So many mistakes which I didn't expect. What did I do? Oh yeah, I know. I see the mistake. What's the mistake? Typical one-off error. Our doc IDs here start with 1. But of course in an index it's -1, so it should be -1 here. Yeah. Okay, and now I have it, and you already said it, so if I encounter the same word twice, here I just set the entry to 1, I should of course have plus here. So if I see it several times, I'm incrementing it by 1. So here's an example, right? I have it twice here, I encounter it, I increase it by 1. So let's do that, and yeah. There we have our term document matrix, and maybe that's a good time to make a break. So 5-minute break, and then we resume. So we are back online. We managed to create a term document matrix and print it. Now let's also create a query vector. So let's, I think that works as follows. We just want to have a vector here. Okay, let's just look at that as well. Let's print it, query vector Q, and let me also print that as a, let's see whether it works. So that's now a one-dimensional tensor. Everything is a tensor in Torch, we already saw that. Oh, my iteration over a... Yeah, okay. Let me just make it a matrix with 1 row. I think that should work. Otherwise, I need an extra function for printing a 1D tensor. So let me just do it like this. Okay, that works good, fine. And let me print some empty lines here and an empty line here. And now let's do the scores. And the scores should now be, yeah, this should work. Q times A matrix product. This is now a 1 times 4 matrix. This is a 4 times 6 matrix. Let's see whether it works. Print scores and print scores. So, yeah, now this is exactly the same matrix as we had it on the slides. We are creating this vector, and now we are doing the matrix product. And let's see whether we get the, okay. There's another problem. Okay, I see it. Yeah, it's somewhere on the slide. So matrices in Torch, you have to say which type they should have. And here I think it implicitly takes, yeah, I'm not sure. I think it assumes here, because I'm specifying only integer, that it's an integer one, but I think in my A matrix above, it doesn't know that it's integer, so it implicitly assumes it's float, or maybe that's also the default when you take zeros. So here now I'm saying type float. I could also say here above take type int and type int here. Would be fine either way, just has to be compatible. Yes, and now it works. And let me also have a new line here. So this should be 212, 311. These were exactly our scores. And the important thing, and that's maybe the most important thing about this whole linear algebra stuff, I did my whole retrieval with a single vector matrix multiplication, right? This is what does the retrieval here. This is my matrix, which I've somehow pre-computed. The vector has been entered. Now I have a matrix and a vector, and now I'm computing all the scores simultaneously with one operation, and this also works if I have 100,000 terms and 5 million documents. It's just one operation. And that's important because this operation is now not done in Python with funny loops and super slow, but it's coded in C somewhere in the background in some package, so it's really fast. So even if this stuff here constructing might be slow, but this here is fast even if it's a large matrix. Okay, back to the slides, and please do ask questions if anything is unclear. And we were a bit further. Yes. So this is how we did it, and it works. And this does not work because here it's a 1D. You can't multiply a 1D with a 2D tensor. So let me maybe fix the slides here. How I did it here is I just made a matrix out of it, a matrix with one row. Little bit of cheating. Otherwise, there would be ways to get it to work too, but that's like the simplest way. Okay, here's another slide where I don't have, let me quickly fix that. And maybe it's on the next slide too, yes. But on the next slide too, oh my. Okay. Oh my, why, how did that happen? I don't know. Let's just go one by one. Okay, so here's one problem. And this I don't show in code anymore. If we do it that way, if we compute the scores, sorry, just with a dot product, then I get a high score just because I have many entries here or high entries here, right? So it's debatable if you think about what's the document about. D4 is kind of about web surfing and beach surfing. And it gets the highest score here because it just has so many entries and a high number here, a high number here. But should it get a higher score than D1, which is only about web surfing, it's kind of unfair. This just gets, because the 2 here is a 2 and not a 1 because there's also beach surfing, but the query is about web surfing. So it's debatable whether these are good scores, and this should remind you of something. I mean, that's why in lecture 2 we talked about BM25 scores, right? These were explicitly designed to handle, I have a bigger document, a larger one, which is also about other things, so some terms will occur more frequently, maybe with other meanings, and I have a term occurs several times, maybe just because the document is longer, and BM25 was balancing this. This was what half of lecture 2 was about. So one way, and this you will do for the first exercise, is just take BM25 scores, and then again take the dot product. And let me just go back to this slide. Now just assume that in this matrix I have BM25 scores instead of the TF scores. And this is my query vector. Again, 1, 1, doesn't have any special scores. Now if I compute the dot products, I will just get the sum of the BM25 scores of the contained words, which is exactly what we did in lecture 2. So just by having a matrix with BM25 score, I will get what I get in lecture 2. And exercise 1 is just doing that. But you have to pay a little bit attention. Okay, I will come back to that. There's another variant. So BM25. Another variant is compute the similarity in a slightly different way, namely as follows. Take the dot product and divide by the length of the vectors. So divide x by this length, divide y by this length, which means divide by the product. So what's this length of a vector? Let me be explicit. They are different. It's the norm of a vector, or length. We just call it length here. We just take the L2 norm here. There are other norms as well. L2 norm just takes the sums of the squares and the square root of that. L1 norm would take just the sum of the absolute values, and there are even other norms. But that's the most frequent one, L2 norm. Sum of the squares, square root. Gives you the length of the vector. Actually, in typical space, two-dimensional, three-dimensional, it just really is the length, the Euclidean length of the vector. So this is just dot product normalized, divided by the length. Why is this called cosine similarity? This is also in, when you do deep learning with text, you will meet this all the time. Cosine similarity, you have two vectors, you want to measure how similar they are, you want to account for different length, you will take cosine similarity. There's no cosine here. Why is it called cosine similarity? Well, and for exercise 2 of exercise sheet 10, I will talk about the exercise sheet in a second, you will use cosine similarity. So you will do the BM25 thing and the cosine similarity thing. Law of cosines, here's the link to the Wikipedia article which proves this law. I will not prove this law. One thing that should occur to you, and maybe let me draw something so that this becomes clearer. Let me draw a rectangle. This is A, this is B, this is C, and let me call this angle gamma. So gamma here is just the angle formed by A and B. Now, if gamma is 90 degrees, not Celsius, 90 degrees, then what is this? What does this become if gamma is 90 degrees? Zero, and then what is this?
Pythagoras.
Yeah, it's Pythagoras, yeah. Pythagorean theorem, I think it's called, I'm not sure. How is it called in English? Yeah, exactly. It becomes the Pythagorean theorem, so the law of cosines, and this you can do with elementary trigonometry, or there's an elementary proof for that, which I will not do. But I will show you that if you assume this to be true, then you can, then we will see how this is related to the cosine. And let me try to do that. Maybe I fail, and you have to help me. Let's assume these are two vectors here. If these are two vectors, then then I think the length of C is just the length of the difference between the two vectors, right? If I would, I think that's true. What's the, so if I revert B and do it like this, then I would get, so if I just turn this into vectors, then A, I think that's true, right? So if I would point the vectors in this direction, then I think C is just A minus B. I don't even need that. I just need the length of the vectors. So if I do it like this, then I have so C is just the difference between the two vectors. A minus B squared is A square, and let me just write the plus B square minus 2. And here I have, if I write this as vectors, no, this is the length of A. Here in this law of cosines, these are lengths, not vectors. So if I'm just cosine of, and let me call this angle gamma. So gamma, I'm calling it gamma, third letter, because it's opposite of C. Of course, you have this law of cosines 3 times in every triangle. Let me do at least a little bit of math here. This is really just writing it equivalently, right? I'm not using any vectors here. I'm just taking these things as vectors and taking their length. And just to clarify, let me maybe put yeah. So what is now one thing you should notice is that let me write that up here. If I take the dot product of a vector with itself, and so this is very basic linear algebra, but I'm assuming some of you might be a little rusty or never fully understood it, so I'm repeating it a little bit. A dot product of a vector with itself is, well, it's just the sum of the pairwise products. In this case, it's product with itself. So you just take x and x again, and pairwise product, you get the sum of the squares. And what's this? This is just the square of the length, right? The square of the length. Wonderful. So if we have the square here, we can write this as, let me just do that here. So this is just A minus B dot product A minus B. And this is just, yeah, this is A times A, which is, yeah, let me do this, A times A minus 2, and this is dot product, minus 2 times A times B plus vector B times vector B, which is, yeah, this is the length of A square plus the length of B square minus 2 times A dot product B. Yeah, so now I have A square on this side and on this side, so it just cancels out. So this here, this is on the left side, and this is also on the right side. So now I have minus 2 dot product of A and B is equal minus 2 length of A, length of B cosine angle. So if I, yeah, so now I have, and let me maybe write that one intermediate step. So if I just cancel these things out. And for the exam, you should absolutely be able to do some basic linear algebra like this. So this is minus 2 vector A times vector B length times cosine of the angle, which means, yeah, the cosine of the angle is A dot product of A and B divided by length of A times length of B, which is just a cosine similarity as defined above, right? of A and B. So the cosine similarity, you typically compute it in this way as the dot product normalized, but it's really the same thing as the cosine of the angle between the two vectors. Right? And for the cosine of the angle, it does not matter how long the vectors are, right? You are normalizing them here. You're dividing by the length. If this vector is twice as long, you're dividing by the length. It's the same cosine similarity. So the cosine similarity adjusts for the length of the vectors. That's very important. And for the exercise sheet and also for understanding, that's also very important. So when you compute the cosine similarity, what you have to do? You have to compute the dot product, easy, it's just sum of products. And then you have to divide by this, this is costly. I have the sum of these squares and then divide by the square root. Here's a very important thing you should understand also for the exercise sheet. So if you want to compute cosine similarity with many documents, so like here, I don't have it on the slides now. I want to compute the cosine similarity of this with this. Now what I can do is I go over this, I compute this dot product times this divided by length of this. Now what you could do is, of course, because you're reusing every time the length of these things, just pre-compute them and store them somewhere. But that's also not what you should do. What you should do is, you can just normalize the vectors. That's what you should do. Yeah, you should just divide each document by its length so that afterwards it has length 1. And let me just verify that for you, that is true, because people sometimes get it wrong. How do you normalize the vector so that it has length 1? Let's just take the length of x prime. So the length of x prime, if I divide it by its length, it's the length of x divided by its length. So this is a scalar factor, a constant, so I can just pull it out of the norm. So this is 1 times x, which is indeed 1. So that's one little proof, right? So if you divide a vector by its length, you get a vector that has unit length, that has L1 norm. And if I have 2 vectors of, let's also check that this here is true. So if I now do cosine similarity, I'm not writing sim here, I just abbreviated it to save some space. So if I now work with the normalized vectors, let's just plug it in here. I have, that's now x prime by definition. It's the dot product divided by the length of the vectors, which for normalized vectors is 1. Right? They are normalized. And now let's just plug in what we did for, x prime is divided as x times, so this is now x times y divided by x times y. Sorry, and this is actually the same as the cosine similarity between x and y. So this is the proof for this, that if you divide by the length, you get indeed length 1. And then you can just compute the cosine similarity between the normalized vectors. It's exactly the same. So what you always do when you want to compute cosine similarities a lot, you just normalize your vectors. And afterwards you can just compute dot product. So you normalize them once, and this also you have to do for the exercise sheet, and then you just compute dot products, and everything is fast. Any questions about this? Okay, here's one more. That's just interesting. Okay, that's also important for the sheet, but that's also an interesting relation here. Yeah, and just look at this part. Again, the animation doesn't work. I mean, we had these toy matrices, 4 times 6. Right? You don't have a lot of zeros here. In a typical large matrix, 100,000 terms, millions of documents, you will have a lot of zeros here, right? And this matrix is huge. You can't store this matrix explicitly. It's just too large. Let me just write that here maybe. For example, let's assume, and that's not untypical, we have 100,000 words, and maybe we have 10 million documents, right? Now I already have 1,000 billion entries in my matrix, right? That's a huge matrix. 1,000 billion. Billion is already giga. If I have 4 bytes, it's 4 terabytes. If I have 4 bytes per entry, so 8 bytes per entry, that would be 8 terabytes, just to store that matrix. But most entries are 0. Most words in a given document only contains a subset of the words. So how you will always, except in our toy code, in the exercise sheet, store a matrix is in sparse matrix representation. Key. And you do it as follows. It's very easy to understand. You just store triples. You don't store the matrix explicitly. You just store like this. So this is now these are the row indices here. Let me just write it here. Nothing of this is complicated, but you have to understand how it fits together. Right? So this, for example, this entry here says that in row 2, let me maybe make it a little bit thicker. So in row 2 and column 3, row 2, column 3, I have a 2, and it's this 2 here. Yeah? So this 2 is this 2 here. Yeah, so you just store the non-zero values and you say, okay, this non-zero value occurs in this row and in this column. That's sparse matrix representation. Super simple. There are 2 ways to store it. How do you sort the entries? I mean, in which order do I go through them? I can go row major, row by row. That's how it's done here. First, all the non-zero in the first row, second row, third row. That's called row major, or column by column. I could also go other ways, but these are the 2 typical ones. Row major, column major. And here is one important thing, also a popular exam question. Make a note. Look how, if you go row major, which is the typical representation, if you just look at the entries which have the same row index, that's just the inverted list, right? 0, 1, 3. Yeah, that's just the inverted list. If assuming the scores are all 1, or you could also store this. This just says this word here, and we are talking about word 0. So the 0th row occurs in documents 0, 1, and 3. It's just where I have a non-zero score, the word is contained. And if I want to also compute the scores, if it's not always 1, also store it. I have tuples of doc IDs and scores. We also had that earlier. So in row major, so this is everything from the first row, or if we go back, right? If I just say there are 3 values here in document 0, 1, and 3, that's just inverted list. right? So row major and inverted list is, and that's not, I mean, it's easy to see, but maybe not obvious that sparse matrix representation and inverted index lists is just the same thing. This is just all inverted lists concatenated. Okay, and you need that for the exercise sheet. Sparse matrices in PyTorch, how you use them. It's very easy. You specify the non-zero values and you specify, I mean, you essentially specify exactly this, these triples, just you don't give a list of triples, but you give 3 vectors of exactly the same length. So here, so this is the first triple, right? This here says value 1 at row 0 and column 0, value 1 at row 0, column 1, and so on. So you just give it as 3 separate vectors. Of course, they must have the same, it's just more efficient that way. And then you call sparse COO tensor, which is a sparse matrix in this case. You say what are the dimensions, and then you give this values vector, and you have to say which type. And the COO simply stands for coordinates. So in the older NumPy, you could say row major or column major, so you could influence in which order it's stored. Torch always stores in row major, which is stores it like an inverted index. Which is a bit funny. So for the exercise sheet, what you will do is you will create an inverted index. From that, build the term document matrix in sparse form, which is internally stored like an inverted index. But then you can do stuff efficiently. And what PyTorch can also do is you can multiply sparse and dense. With NumPy and SciPy this wouldn't work because the dense stuff was in NumPy, the sparse stuff was in just a second. So you can do that. You can do Q times a sparse. Here's the sparse matrix, that's the dense one, it works. Yes, please? That's so you are saying when I permute all 3 in an arbitrary way, does it make a difference?
So the rows stay the same, but the permutation of the rows.
Yeah. I'm not sure. I mean, you could just give each vector, you just pick any permutation of the size of this and apply it to all 3. Then it's the same representation. And the question is this call just as efficient? And I don't know, but that's a very good question. And in particular, is it the most efficient if you have sorted it in this way as I've done here? This is like row major sorted, right? First row 0, then row 1. Please look it up and tell me. It might not be super easy to find out. Yes?
I have another question.
Yes?
I think related to it. Does storing the matrix in row major or column major, does it affect the efficiency of our dot product calculation?
Yes, absolutely. It's very important for that. I mean, it's now internals of. Yes, it does. And it depends on what you do more often. So it kind of what gives you a hint. Here, for example, here you see that it's not so easy, right? This is now a topic. I could say a lot about that. I mean, what do you do here? This matrix here, you go row by row, and it's always good in memory when you scan over things, and just imagine this to be huge matrices when things are close in memory. So when I'm going over these values, it's good when they are consecutive in memory, which means this particular product, if this would be a huge vector and a huge matrix, would work well if this is consecutive in memory and if this is consecutive in memory, which means for this particular product, it would be good if this were row major and this were column major. And so you already see the problem. If you multiply matrices, you would like to have the one in this order and the other one in that order. And now it depends on what you do, which order is the best. And this is further complicated by, so I don't know how Torch does it internally, but Torch is of course made for being executed with a GPU, where it's still done completely differently. I mean, big matrix multiplications are done on GPU nowadays. But it gives you a hint that it's a very complicated, complex topic. So you might even consider for best efficiency to store it in both orders, if it's just created once and then used a lot, and you want to use it on the left or right side of matrix multiplication. So very interesting topic, but yeah. And I don't know how much PyTorch is optimized for CPU, for fast CPU computation. I know it's fast for GPU. Okay, so we have one more part, which is not hard. Will take 10 minutes, but you need it for the second exercise. And let me quickly go through these slick slides, and sorry for that. That's probably one slide which I copied, and then it always had but that's, I like these meditative tasks a lot. Just write for my... So, it's not hard, so don't worry. Word embeddings, and it should actually be called word embeddings, but I won't change the title now. So the words in a collection, we already had this, are called vocabulary. So for example, for our running example, internet, web surfing, beach. Typically you would say it's a set, the order does not matter, but let's give it an order. If we give it an order, and we did that in our code, then every word has an ID. So, and the order is not really important as long, of course, as we stick to it. So if we just say, okay, this is the order of my words, then one is always web. So it's just I take any order and stick to it, and then my words have IDs. That's nothing new. We already used that. And now, this is also not new. We have already seen it. I just give it a new name now. So in the context of learning, this is called one-hot encoding. I can now write each word as a vector like this, and we already kind of saw it for the query vector. But now let's not take a query, let's just take our individual words. So I have a document, a vocabulary with 4 words, internet, web, beach, surfing. So I write each word as a vector, like the document containing only that word. Nothing really new. And this is called one-hot encoding. So I have an ordered. Why is it called that way? Well, I have a large vector with only zeros, and there's a 1 at exactly one place. And this doesn't have to be a vocabulary. You have any set of elements, 1,000 elements, and you want to give each element a distinct vector. Well, just make vectors of length 1,000, and the first element has 1, all zeros, second has 0, 1, all zeros, and so on. So, yeah, we have already seen this, but here we just give it a name. This is called one-hot encoding. So I give each word a vector. Oh, and this is not blue. That's terrible. We can't continue before we make this blue, or everything will crash. So, how is one-hot encoding? We kind of used it implicitly. I mean, if you take, and there's one more idea here, so please stick with me, stay with me for 5 more minutes. It's really not more. If I take I have a document, so this was one of our documents, I think it was the 4th one, internet, web surfing, beach surfing. And it had this vector, 1121. as a column vector? Well, it's just the sum of the one-hot encodings of the words, right? I mean, it's almost trivial, but that's how it is, right? Here are the one-hot encodings of the word. I have surfing twice, so that's why I have a 2 here. So that's one way to see the document vectors. You just have a vector for each word, which are these vectors which we have seen. I sum them up, I get the vector of the document. So in this view, words are vectors, documents are vectors, and I just get the vector for a document by summing up the vectors of the contained words. And the same is true for the query vector, right? Let me just go back once more here. My query vector here, and a typical query vector contains few keywords, and each of them once. You don't type the same word twice in a query typically. So a typical query vector, it's also just the sum of the vector for web and for surfing, and so it has a 1 here and a 1 here. Typical query vector has a few ones, otherwise zeros. Now, here's one property. It's trivial, but we will see something interesting on the next slide. If you do it that way, then all pairs of words are equally different, right? If you take their dot product or their cosine similarity, it's 0, right? Because they have the ones in different positions. So, yeah, I don't even have to write it. I take the dot product, it's 0. Internet and web, internet and beach, the dot product is 0. Any pair of words which are not the same, the dot product is 0. And wouldn't it be nice if words that are similar have a higher similarity than words that are similar, that somehow do not mean the same thing? So wouldn't it be nice to have vectors here such that the cosine similarity between these two is kind of high and between these two is kind of low? Well, and that's what word embeddings are. So word embeddings, it's just the same. I have a vector for each element from my vocabulary, just it's not of this all zeros and just one type. And now I can also play around with other things. The dimension of these vectors does not even have to be the dimension of my vocabulary, and it typically is not. So for exercise sheet 10, we give you documents which have a vocabulary of over 100,000 words, but we only use 300-dimensional vectors for each word. And now, now it can't be that they are all pairwise orthogonal because I don't have enough dimensions. Now I have exactly this property. And before we close, let me write a little bit of code for that to show it to you and also to how easy it is. Now, how do you compute such vectors? Computing these vectors is trivial, right? They're so easy. But these other vectors with the property that now vectors of words which mean the same thing are kind of similar, have a small angle between them. Others have a larger angle. How do you do that? Well, that's a lecture which we had to throw out. It used to be there in the previous years, if you are interested. There are many ways to do this. We just didn't have time for it this time. So for the exercise sheet, we just give them to you. And let me just, that's the last code I write, but it's very nice. So let me just write embeddings test.py here. Need a few more minutes. Let me just copy, and of course they are linked on the web. Retrieval, 24 data sets, embeddings. Yeah. So now I just copied 2 files here. Embeddings fast text. This is from Facebook. Embeddings computed by Facebook for over 100,000 works. And here's just random vectors. You will see in a second why. And let me just, quickly write some code here, which just read this file Yeah, and let me just do some argparse stuff here. Okay. Argparser, I want to add an argument. What do I want? Embeddings file. Yeah, path to embeddings file, and let me, no, I want to parse it. Okay, now I should get my if name. Oh, I had, and please tell me when I make a mistake. So now I have a, yeah, so I need an embeddings file now, and let me just take the, okay, and now let me load it. Embeddings is, okay, torch, now I need torch again. How do I load the file? I just say torch load embeddings file. So now I'm loading the embeddings file, and maybe I should write it here. Okay. So I always have the 1 second. Now I'm loading them, and now what's written on the, it's really just a dictionary. It's a dictionary of words to vectors. So let's just, let me just, internet, embeddings, and what else do I have? Web, surfing, no, I wanted surfing, and beach. I don't know if the words are there, but let's see if they're there. Yeah. So it's very easy to just get the, and now I have these, maybe print length of, yeah, let me just see one of these vectors, how long is it? 300, so it's a 300 dimensional vector. So you see it's very easy. I just load this file with torch load. I want an embedding vector for a particular word. Just use it like a dictionary. Now this is a vector of dimension 300. And now let's just print similarity, cosine, similarity between internet and web. Okay, and I don't have to, I think. And now how do I compute the, I think there's cosine similarity here. Yeah, you can just call it chord, torch, cosine similarity. Here I'm just using 2. I don't have to normalize anything. Let me just, okay, it's a tensor, a 1 times 2, so it's 06826. And let's maybe surfing and beach. No, I want internet and beach maybe. Internet and beach. So these are kind of unrelated. Yeah. So you see a much lower score, and let's maybe also do one last between beach and surfing. They should be kind of, beach and surfing have something to do with each other. They are not exactly synonyms, right? So you see it's fairly easy to use. We don't know how these embeddings were computed, or I didn't tell you. So you see, these kind of have these properties, right? I take the cosine similarity, internet, web, that's pretty good. Beach and surfing, not quite as high, but still related, internet, beach. And you don't see they don't go towards 0 or 1. That's typical, because that would be hard, but there is some, there is some pattern here. And if I take the random ones, yeah, I just get kind of, here it's 0 for some reason. And you will do that for the exercise sheet. So as a last thing, let me just show you the exercise sheet. I hope it's there. It's a simple but important exercise sheet. So first, do the evaluation, please. The first exercise is take exercise sheet 2, take the code and just create the sparse matrix. And do the same as an exercise 2, so just simple search engine, but with matrix vector multiplication. It's a nice exercise to get into this. And exercise 2 is just do similarity search. So you have a movie as an input and you use our edit distance stuff to search. It's very easy. And then you just find similar movies with just find the movies with similar vectors. And we give you that. It's not a lot of code and it's surprising how good it works. So really nice exercises to get into this stuff. So also in the new year, we continue our tradition of going slightly over time. But you had 2 free weeks for that. Any questions for now? There are just 2 more lectures with content. If you didn't do the exercise sheets until now, start now. Okay, that's it. See you next week. Bye.